So first of all, let me thank the organizers for this wonderful conference and the program. I've had a lot of fun so far, and I look forward to the rest. So today I'll talk about a work based on the recent paper with my collaborators at UC San Diego, Anish Manohar and Ella Ridgway. So in this talk, I'd like to ask the following question. So can we analytically solve the full binary dynamics in perturbation theory or even non-perturbatively? So in order to answer this question, we really have to analyze the fundamental properties of the binary system. So consider the simplest scenario where we have the so-called conservative dynamics. These are governed by the so-called effective potential. In the center mass frame, this is just a function of the radius r, momentum p squared, and another rotational invariant variable p the r. And we have a nice framework for effective field theory. And as a particle series, then I can just turn on the crank and calculate this effective potential for n log gr order by order in the post-Newtonian approximation. But we can ask, is there any symmetry that we can use to solve this system? So as many other talks explained already, it's much more convenient to think about the analogous scattering problem, where for the initial and final state, the space-time is flat. So it's natural to think about this as relativistic scattering, and we're not constrained by Virgo theorem anymore. So we have the relativistic scattering angle, which is the physical observable here, and we can match to the effective potential by effective field theory. And this is naturally give us an order in velocity effective potential. But there are actually two important simplifications that I want to emphasize. First is that the scattering angle is really a function of angular momentum J and energy E, which map to the Mandelstam T and S in amplitudes language. So this translates into the radius R and momentum P squared in the effective potential. So from here, you immediately see that this third variable, P the R, is actually a pure gauge artifact. So we can move that entirely. So that simplifies your effective potential a lot from this approach. Second, Lorentz invariance tells us that we can boost to any arbitrary frame. So we can go to the rest frame, where in the test particle limit, this test particle is governed by the geodesic under background spacetime. But even with a finite mass ratio, the kinematics is simply easier to work with because the energy is proportional for this moving particle. It's proportional to this relative boost, sometimes called gamma or sigma, but it has a very simple relativistic expression. Whereas in the central mass frame, the momentum p squared doesn't have a linear relation to relativistic invariance. So these are the two immediate implications you can use from this paradigm. So now we really have a synergy from two different fields. We have the scattering amplitudes using generalized unitarity, double copy, and effective field theory, and combine these two areas, then we march on to the precision frontier of the binary dynamics. So as a benchmark, let me consider the high order potential without spin. So there has been tremendous progress in recent years. For instance, in the traditional methods, we have all the way to the full potential contribution at 5p and older, and some partial results at 6p. In the past few years, we also calculated in the amplitudes and EFT approach, the order g cubed and g to a fourth to all orders in velocity. And we also find perfect agreement with the traditional methods. So this is really exciting. However, if you watch any of the simulation from LIGO, you'll notice that the binary, they don't stay in this perfect circular orbit forever. So they gradually inspiral into one another. And this is caused by the gravitational radiation because they carry away energy and angular momentum. So effectively, this looks like a friction, which described by a so-called radiation reaction force, first calculated by Virgo and Shen more than 50 years ago. And this is really not a small effect. So these start at 2.5 p.m. order, And as we march on in the conservative part to 5, 6, 7 p.m., we really have to adjust this dissipative dynamics in order to have the full description of the binary motion. But this turned out to be very challenging. For instance, the state of ARN, after 50 years of Virgo and so on, we only know the partial result at 4.5 p.m. order. So just like the conservative case, people also thinking about the analogous scattering problem. So all the way back to Kavli and so on, in modern paper is initiated by Goldberger and Ridgway a few years ago. And there has been tremendous progress so far on this dissipative dynamics in scattering. So let me not read through all these achievements. And these are mainly in the context of scattering. But if you assume adiabatic and aligned spin approximation, then we also have a nice boundary to bound map, as explained by Raphael this morning. But I'd like to ask two questions. First, how do we convert a lot of this impressive progress to the case of bounded binaries? And after all, these are the sources that are more relevant to the LIGO detectors. And second, just like the conservative case, can we leverage symmetries again for the dissipative dynamics? And in this talk, I will argue that for the dissipative dynamics, you simply have to lift the Lorentz invariance into Poincare invariance. So Poincare invariance means that we have the conserved charges from translation and rotation, which are the linear and angular momentum. And as the gravitational radiation carry away these conserved charges, this back react to the binary system. And because of effective field theory, we know it's governed by the very same radiation reaction force. So without spin, the radiation reaction force has two components. It's on a 2D plane. And we have two observables which uniquely fix this radiation reaction force. So this answers the first question I raised earlier in the previous slide. And so now you really convert the question into how do we compute this energy and angular momentum? So energy is straightforward. It's just the cross-section weighted by energy. However, angular momentum, on the hand, is not so trivial. And at order G cube, we have the energy, radiated energy, but the angular momentum remains to be unknown at this order. So that will be the goal for the rest of the talk. But let me first go over to how to calculate radiated angular momentum first. Okay, so if you consider a scattering scenario where we have two particles in, some collision, and with two outgoing particles, and this is the radiation more or less centered around the retarded time t equal to 0. So the total linear momentum is simply integrating the stress energy density over the entire space. So the momentum density is given by T nu 0. And angular momentum, on our hand, we know that it's R cos P in relativistic physics. For relativity, it's given by this rank 2 antisymmetric tensor. So the R cos P, R is replaced by this X mu and symmetrized by the momentum density T nu 0. And of course, we're definitely not the first one thinking about calculating angular momentum. And if you open a textbook, there's the known formula for radiated angular momentum. But you can immediately ask the following questions. Since it's written in terms of the standard transverse stress component of the metric, so how do I see that this formula is gauge invariant when I change a different reference? And second, we know that angular momentum naturally is a rank 2 tensor, but this only gives you the spatial part of the angular momentum. So why can't we covariantize this standard formula? So okay, now so let's just go back and see how we can derive these formulas by ourselves. So for illustration purpose, let me also give you both the gauge field and the graviton field. So from particle theory, we're more used to writing the waveform in terms of momentum space. So these radiation over fields, they're sourced by this current J nu, or in the gravity case, the stress energy Schroeder tensor, which includes both the matter contribution and the self-gravitating part. And because the fields, they're ultimately not gauge invariant, so we have some gauge-dependent prefactor here. And the details are not very important, but for instance, if you're in Lorentz gauge, then this P nu is really the eta nu. And then we integrate over the phase space is this dk tilde here. So two important remarks here. First is that it's very tempting to impose the transverse projection, but don't do that, especially if you're looking at the scattering sources. We will have the so-called Coulomb mode. So you don't want to do that, and I'll explain this later. And for the same reason, you should really treat this part as a classical background. So I'll avoid using creation and analyzation operators. Okay, so having these fields in the momentum space, now we just plug into the expression for linear angular momentum. So let's consider linear momentum as a one-up. So when you plug this in, you'll find out that the resulting formula is very simple. So this part, the quadratic part in the Schroeder-Schwarz energy tensor, is simply the polarization sum of your waveform, or in particle physics language, this is the cross-section. And you weighted this by the momentum, k nu, integrate over the phase space. So, okay, this totally makes sense. That's the linear momentum. And you simply do the same procedure for angular momentum. And then we found that there's this new formula for the angular momentum. And as you can see that when we write down the fields, there are gauge-dependent prefactors. And then also, when we integrate the charge, we pick a particular time slice. But all these dependence drop out. And this final formula is covariant, as it should be in relativity. And we claim this being a new formula. So let me unpack this new formula a little bit. So you might notice that the first two terms, they're very similar to the linear momentum, except that there's this L nu operator, which is a differential operator, sometimes called orbital angular momentum. And the reason that these two structures are identical is that these simply governed by the Poincare algebra, because the angular momentum, it depends on the origin of your coordinate. So when you do a shift, the angular momentum should shift in this way, proportional to linear momentum. And because this G nu pick out the phase, so therefore in these two terms, they have to have the same structure as the linear momentum. So that already constrains the first two terms. And also this stress energy Schroeder tensor, they are not gauge invariant. There's a residual gauge freedom you can do. And this second term is gauge invariant by itself, but the first and the last term, they are not gauge invariant by itself. It's really the sum with this precise coefficient that you cancel this gauge dependence. So sometimes in the literature, people refer this first two as orbital part, this part as a spin part. But as you can see, obviously here, because they are gauge dependent. So for massless radiation, there's no gauge invariant separation of orbital and spin. You should really only consider the total angular momentum because there's only one generator for the space-time rotation. Okay, so now with this formula, we can now just simply calculate this Schroeder-Schwarz energy tensor or the sources and compute the radiated angular momentum. So now let me consider zero order, leading order, which is given by the zero frequency limit. And it goes by many other names like Weinberg-Soft theorem, memory, etc., etc. So the reason that we only care about the zero frequency limit for the leading order is that the leading order stress energy tensor is given by free particle with constant velocity. So when you do a Fourier transform, it translates into a delta function in the frequency. So if you want to interfere with this contribution, you also only care about the zero frequency limit of the waveform from collision. But if you consider this limit, then you zoom out the time scale. So all the collision now happen exactly at this origin of the space-time. So the resulting wave is like this, centered at retarded time t equal to 0. And the collision give you a step function in time, which Fourier transform into this 1/omega plus I epsilon. And so this gives you the zero frequency limit. And two important remarks. First is that These free particle mode, or sometimes called the Coulomb mode, they're definitely physical even with zero energy, and they're simply the Coulomb field you learned in high school. And back to the point I made earlier is that typically we assume the fields are transverse, but they're definitely not transverse for this particular part, the Coulomb mode. And just go back to the high school E&M, the electric field, they're along the radial direction, so they're not transverse at all. So you should not impose that projection. And for this deflection, this is really valid for any arbitrary deflection. So as we learned from Weinberg many, many years ago. So now you can plug this result in and see what the radiated linear and angular momentum. The linear momentum is zero, trivially because we consider zero frequency limit. Angular momentum, on the right hand, when you combine all these frequency factors, you'll find out there's a finite contribution in the very end. And this looks very weird at first glance because how can the wave carry angular momentum but not energy? But there's nothing really wrong with this result, because if you think about this in terms of classical field theory, for instance, in E&M, angular momentum is r cross p. P is the Poynting vector given by E cross b. And for this interference term, you only have 1 over r cubed scaling at large distance. So when you integrate over the two spheres, you'll find out that the momentum density is zero, or the energy density is zero. Sorry, the total energy is zero. But for angular momentum, because it's r cross p, so you have additional r factor, which give you a non-zero total angular momentum in the end. Okay, so now we can simply plug in the result and calculate the components of this radiated angular momentum. So the details are not important here. The important thing is that it only depends on the leading order deflection angle theta. And this is completely model independent. You can plug in whatever theta you have in your theory with some spin, without spin. We can add additional particles like dilaton, supergravity, etc. It's a universal formula. And one thing very interesting is that for radiating energy, it's positive definite because it's energy times cross-section. But for angular momentum, on the other hand, it really cares about whether it's attractive or repulsive, because everything else is positive. But if theta is negative, then you have a negative radiated angular momentum. And I find that quite amusing. So, okay, so this is leading order G-squared result, and we can compare with the known literature. So at G-squared, we agree with Stamore. And soon after our paper, there's a very nice result from De Vicchia, Heisenberg, and Brussel. They calculate this for arbitrary deflection, and we also fully agree. And the J0I component at G-squared, we also agree with some Grada and Lobo and Sam module a potential extra term, and Sam will discuss this more tomorrow. But one thing we really disagree is the textbook formula that I showed earlier. And we did the calculation ourselves, and this also calculated this in the rest frame. And we all agree that our formula disagree with the textbook formula. So we're quite nervous, and as we should be, because we disagree with a very well-known formula. So what to do is to analyze this situation carefully. So just to recap, the difference is that in the rest frame, in the center mass frame, so center mass frame, everyone agree. So two formula give you identical result. In the rest frame, however, textbook says that the rest frame on the ratio between radiating angular momentum and the original angular momentum, the ratio is 1. It's the same as the center mass. In our formula, we said that there's a factor of half between the rest frame and the center mass frame. So we want independent tracks that does not rely on any of the technical details I mentioned before. So we'll use two possible tracks. One is to consider general covariance, and second is to use the known radiation reaction force. So in terms of general structure, if the angular momentum, there are Lorentz covariant, that should be a function of all the possible vectors in your initial problem. So namely, we have momentum P1, P2, the initial impact parameter B1, B2. So you can decompose these two impact parameters into a difference delta B and the average B bar. And then you can write down all the possible tensor structures. And from Poincare invariance, we know this average B bar will translate under space-time translation. And from the algebra, we know it has to have identical tensor this coefficient as a linear momentum. And after that, we have other structure where all these F1, F2, F3, G1, G2, and H12, these are unknown function as a function of this scalar invariant. So this is what we call form factors, which is a common way to parameterize non-productive structure, for example, in the hadronic physics in particle theory. But this assumption is very general. We only assume the Lorentz covariance, Poincare algebra, and the particle symmetry between particle 1 and 2. So now we can consider the zero frequency limit, which simply set all these to 0. And for the JZ component, it only depends on this term. So from here, we conclude that in the center mass frame, the ratio between radiated angular momentum versus the initial one is given by G1 plus G2. And the rest frame is given by G2. So once you have the rest frame, and at this order, it's the same, it's symmetric between particle 1 and 2. So we conclude that in the center mass frame, we should get a factor of 2 relative to the rest frame. And there's no, so this is a very general assumption and does not rely on any details of the system. And this is really a non-productive result. So a different check is that we can use the known Bergstrom radiation reaction at G squared. So it's given by the following, where we have a acceleration of particle 1 and 2, which are exactly opposite, regardless of the mass ratio. So this is really weird. It kind of blew my mind when you first think about this, because for Newtonian physics, F is G and N over R. So the acceleration of the heavy particle should be negligible in the large mass ratio. But this radiation reaction force tells you exactly opposite, as equal and opposite, no matter how large the mass ratio is. So you can simply calculate this equation of motion, and you just involve with time, and you find out that the initial and final state have exactly the same energy. But the net effect of this force is that it shrinks the impact parameter exactly the same, no matter what the mass ratio is. And this is kind of, so the heavy particle is not decoupled at all. And this is similar to the Yukawa coupling in particle physics, that the heavier you are, you have stronger interaction. So in this case, the heavier you are, you tend to radiate more. So therefore, the force, the acceleration is the same and does not decouple. So using this as an input, all we need to know is that if the impact parameter shrink identically between the two particles, in the central mass frame, I have two copies of angular momentum loss. So ratio of radiated angular momentum versus the initial one has a factor of 2. While in the rest frame, because this particle is not moving initially, so after scattering, even if the impact parameter shrinks, there's no change in angular momentum from this particle at rest. So from this simple derivation, we find out that there's a factor of 2 difference between the center mass and the rest frame. Now, even in the extreme mass ratio limit, which these two frames are nearly degenerate. So what we can conclude from this derivation is that the back reaction is really important. Imagine this is a heavy black hole. The back reaction really, you have to take into account the back reaction in order to get the correct answer. So we conclude that our formula agrees with covariance and the known radiation reaction force. So after cleaning up this conceptual issue, now we can move on to the precision frontier, calculate the angular momentum loss at G cube. So the linear momentum has been calculated by these authors, so Julio and Michael Ruf are in the audience. And for the angular momentum, it has 2 contributions. And the zero energy contribution has the following diagram. It has a free particle part interfere with this 1D waveform, which is not known so far. However, as we show that from the soft theorem, this part is actually the easiest one to calculate because the same calculation, you just need to change the impulse to g squared, which is known since the 80s. And for this finite frequency part, we can bootstrap the waveform by double copy, generalized unitarity, and using KMOC to get the waveform. And the integration is not too difficult. We resolve the series after expanding this to high enough order. But of course, it would be great to use some modern collider techniques to do this rigorously. But the final result looks like this. The radiated incrementum has a finite energy in the zero energy contribution given by this function of transcendental weight 1. And this is the result calculated in the rest frame, which is easier. But if you want to go to a center mass frame, it's important to take into account Poincare algebra, which introduces the radiated energy, which is given by this function, the curl E sigma. And this relation relate the radiated incrementum to the radiated energy is actually first found by Bini-Damon-Girardico about a year ago when they considered G2-4 scattering. And here you can see that we see this directly by considering the Poincare algebra and the mass scaling in a simple rest frame. So having this new result, we can also use the idea of radiation reaction. So we want to check with literature, and when we expand in velocity, the first three order completely agree with the result from Bini-Damon-Girardico. But on top of that, we extend this to orders in velocity. So what we cover is that all the Poincare charges at g squared and g cubed. So now using this as an input in the previous linear momentum energy loss result known by others, we can make a non-trivial new prediction for the G2 force impulse. And because this is due to the radiation reaction, so we can factorize the problem into simpler results. And this transverse part of the impulse, it has the conservative contribution and the dissipative contribution, which you can first separate into the even in velocity and odd in velocity part. So our result give this prediction odd in velocity. So this the conservative part we have calculated directly about a month or two ago. So the only thing unknown is this even in velocity dissipative part. So the part I like the most in this thing is that we really use mostly leading order input or tree level input, where we can make new prediction as 3-loop or G2 force, and thanks to the idea of factorization from effective field theory. So now having this input, we can combine all the known results. We have the conservative part bootstrap from scattering angle, dissipative part bootstrap from the loss of energy incrementum, and we have the full equations of motion at g cubed and G2 force to orders in velocity without using Einstein equation at all. So once we integrate our gravity, now we can really just put this into Mathematica and see the motion of the binaries. So if I start with the energy in incrementum like this, and we can just let this evolve with time. The blue one is the one only have the conservative part, so it's in the perfect circle. But the red one is the one turned on radiation reaction force. So you can see that you have this in spiral pattern, and this energy incrementum, you can see that it decreases over time when you turn on this in spiral. But just a caveat, this is only for illustration only. Don't really trust the plot from series, at least the one from me. So the real reason I want to put this video is that hopefully I can make some of my LIGO series, my friends from LIGO theory interested. So this is a plot where they put a lot of work to compare the PN conservative dynamics with the known EOB and numerical relativity. So you can see that the convergence is still not very good. So one thing I definitely look forward to is to see whether including this dissipative part, whether or not, like how close can we get to numerical relativity. So let me wrap up, and let me not read through these bullet points, but I want to emphasize that dissipative effect is an important part of the full dynamics, And we can calculate this from scattering amplitudes and EFT based on Poincare algebra, Self theorem, and modern techniques. And we can reach the state of equational motion from this scattering amplitudes and effective field theory. So I'll stop here. Thank you.
Thank you, Chia-Hsien. For that, that's the question.
Hi, Chia-Hsien. Thanks for a great talk. So you pointed out these even in velocity radiative contributions to the impulse. So these supposedly come from radiation reaction squared, and you have the radiation reaction force. So could you, in principle, compute this by solving the classical equation of motion in some way, or do we really need to do a new calculation to get this?
I think, yes. So short answer is I think we need an in calculation because the corresponding observable here would be energy and angular momentum for loss at g through a force. So if you want to match the equation of motion, you should calculate all the Poincare charges, match that so you get the new radiation reaction force at g through a force, and then take that involved with time and see if you see what kind of angle you get.
I see, but in principle, we only need the energy loss and angular momentum loss at g to the fourth. Is that enough? Okay.
Yeah. Or you calculate this directly by camera. So that's another approach.
Great, thanks.
Yeah, could you talk about the BMS ambiguity that you pointed out in your slide that you didn't want to talk about?
Yeah, so I think you're asking me to open a can of worms.
Yes.
Yes, yeah, I thank you for that question. So yeah, we gotten a lot of feedback from other friends about this BMS ambiguity. And yeah, so there are a lot of common concerns for angular momentum. So I think it's a great, maybe I can take this place to expand this. So there are a lot of questions you can ask. First is that it really bothers a lot of people that the energy, the radiation can carry no energy but angular momentum. And second is that the angular momentum seems like a IR divergent quantity. So you can ask, is that really IR finite due to the 1/r potential in 4 dimensions? And you can also ask, is that when we take the zero frequency limit, the Fourier transform kind of sucks because it has a delta function, step function. So there are a lot of subtleties you have to worry about. And finally, it's the BMS ambiguity that a lot of people also ask. So it's important that you separate all these issues and try to do a calculation and settle down each of them directly. So we try different theories. We have scalar theory. So in this case, we have a fixed Minkowskian spacetime, no gauge freedom. So you simply write down the wall line action and just calculate equation of motion. We take the momentum space formula we have, we calculate answer. So we want to avoid this distribution function, so we calculate this in Persian space. And you can also derive the radiation reaction force in the scalar field theory. So we have this cell force from radiation from the scalar radiation. And in particular, this radiation reaction force is not derived from 1/r expansion and also apply to arbitrary trajectory. You're not assuming a scattering scenario in the very beginning. And finally, you can also apply Benida-Moore relation, and as shown already by this nice paper on equal to A, and we find all agreement in the case we checked so far. So this is really a case there's no ambiguity, no gauge freedom, and fixed spacetime. So now you march on to the next level. I turn on the gauge freedom. So electromagnetism, the spacetime is still completely Minkowskian, but there are gauge freedom. And just do this in parallel. We have the momentum space formula, Persian space calculation directly for the J nu. And for the radiation reaction, we have the well-known Abraham-Lorentz-Dirac force given by this formula. And we also have the Benida-Moore relation you can test for classical E and N or equal to A. And again, we find agreement on all cases. And you do the same for gravity. And as I explained earlier, we also find agreement. So now using this calculation, we come back to address the issue I mentioned earlier. So the first three, we can all address them basically in classical, based on scalar theory only. So in the scalar theory, we definitely see zero energy radiation, but with finite angular momentum. And the radiated angular momentum is finite. And a simple argument is that the R divergence is caused by 1/r potential. But this 1/r is only coming from tree level, which is purely conservative. And as we know, conservative part doesn't change the J nu, the angular momentum. So this R divergence doesn't contaminate the radiated angular momentum. And finally, we also have the distribution function issue exactly in the scalar theory, and we find full agreement. And now come back to the final question, which I'm not sure is whether or not there will be BMS ambiguity on angular momentum. The only thing I can say right now is that we do this radiation reaction force calculation in EMN and GR. Both cases we find agreement. So I don't know whether BMS will change the story or not, but the BMS ambiguity has to adjust with this match from the well-known radiation reaction force.
Really interesting stuff. I'll have to ask you a bunch of questions afterwards that aren't precise enough for this forum. But one thing I could ask now is the claim that there's this factor of 2. In practice, does that mean you compute radiated angular momentum in rest frame, you multiply it by 2, and you say that's the answer in the center of mass frame? Is that simple?
To leading order, yes.
To leading order in what?
In G. So,
but okay. So you're going to have corrections?
Yeah. So the rest frame. So this is the form factor I mentioned earlier. The G1 and G2. They are not Newton G constant, but just 2 form factors. So at G square order, G1 and G2, G1 equal to G2. So you literally just get a factor of 2 to orders in velocity.
Is dividing it by the total playing a key role in this factor of 2? No, on the previous slide. Yeah, any slide with that ratio.
Yeah. So yes. So this B is the original impact parameter. So yeah, it's important that you take the ratio because the velocity is simply different once you boost. So you can't compare these two directly.
Okay, but when you boost, you use the standard Lorentz boost for the angular momentum. I think I'm missing something. If it's truly an angular momentum vector or element of a tensor, it has a Lorentz transformation behavior, right?
That's right. That's right.
Does it obey that?
Yeah. So this form factor are designed precisely to simplify this question. So write down all the possible tensor, the 4 vectors. You put the anti-symmetric combination, obey the covariant algebra, and ask what's the most general form you can write down. And if you can match the result, so for instance, if I calculate the JZ component and J01, that would fix in the linear radiated energy, that fix all the form factors here. So if you calculate any other component, if you agree with this form factor, then you're consistent with covariance. If you disagree, then yeah, either you're in trouble or this assumption simply breaks down. So.
Yeah, thanks for a very nice talk. So this relation, also the factor of 2, that must imply something for the J01, J02 components, right?
Right.
If you boost from the rest frame to the center of mass.
Yeah, so yeah, I have the explicit here. So this is a JZ component of what we call J12. So this has a relation with the factor of 2. The center of mass frame and the rest frame, and also they have this relation. And this relation is basically coming out as a consequence of the form factors.
We still have time for more questions. Ah, yes, on Zoom. Gilbert?
Hi, Chia-Hsien. Thank you for the very nice talk. So I was wondering, like, why is it that you guys didn't just compute the radiated angular momentum, just computed the angular impulse using just KMOC formalism, where, as the operator, just take the quantum mechanical operator inside the KMOC formula and then just take the classical limit? Like, would you expect to recover your formula just from KMOC?
Are you, just to understand, so you're asking about the radiation or you're asking about the matter?
The radiated angular momentum.
Right. So, yeah. So this formula, so it's basically you can import this into KMOC. So there are two ways of doing that. One is you say, oh, you simply extract this the pseudo-stress energy tensor by KMOC, like just like what you extract the waveform. And once you have that, it's purely classical. You plug in here, so you get identical answer. Another way you can try to do, at least for finite energy, is that you can view this as an operator. In that case, you can really turn this into creationization operator. Then you sandwich with the classical state. So that's another approach that you get the radiative charges.
So thinking of it as an operator, you mean like saying that is like the operator for angular momentum in quantum mechanics and just put it inside KMOC formula?
Yes. So in that case, at least for finite energy, you can basically replace this as creationization operator. T star then is like A dagger, T is like A, and then it's just sandwiched with the states.
Okay, thank you.
I guess that would just give you the order GQ part naively, right?
Right.
But if you use amplitudes around the background, you'd get the order G part as well.
Yes.
Thanks.
Right. This would be like a background interfere with the fluctuation around background.
Okay, I see no further questions, so let's thank Chia-Hsien again.
Thank you.